Okay, so inequality proofs by induction. Just a few little notes that I'd like you to remember, okay? So first of all, if A is greater than B, then A take B is greater than 0. Basically, bring that B over, A minus B is greater than 0. So that's something that we're going to use, okay? A lot of the time we're going to get that it's greater than 0 or less than 0, okay? And something else really important is that any number to be squared is always positive, okay? Anything to be squared, no matter what it is, as long as it's in brackets to be squared, that's always going to be greater than 0, okay? And one other thing that I just want to remind you, can you remember what 5 factorial is? What does 5 factorial mean?
1 by 2 by 3 by 4
yeah,
by 5.
Lovely. So that means 5 by 4 by 3 by 2 by 1. Okay. Now another way of writing 5 factorial is 5 by 4 factorial. Because that's the same thing. Same thing. 4 factorial is just 4 by 3 by 2 by 1. Okay. Now this becomes important if we have, for example, n plus 1 factorial. Well, n plus 1 factorial is n plus 1 by n factorial. Here it's 5 and then you reduce it by 1. Here it's n plus 1, so when you reduce it by 1 it just becomes n. So that's going to be important in one of our examples. Okay, so just remembering what factorial means. Okay, so let's start our examples then. Can I get rid of the board? Okay. Okay, prove by induction that 2 to the power of n is greater than n squared for n greater than or equal to 5. Okay, in this scenario n is greater than or equal to 5. Okay, before we always had n is greater than or equal to 1. So we've proved by induction, we know we have our 3 steps. The first one is prove true for n equals. Now we've always done 1 because they've said for all values of n. In this question they're telling us n is greater than or equal to 5, so the first number we're proving it true for is 5. Okay, so 1, prove true for n is equal to 5. Okay, so that's going to be 2 to the power of 5 is greater than 5 squared. Well, 2 to the power of 5 is 32. That's greater than 25. That's true. Our second step for induction is assume true for n is equal to k. So we're assuming that 2 to the power of k is greater than k squared. Okay? But that is only if k is greater than or equal to 5, so just don't forget that little part there. Okay, we're only showing and assuming for k is greater than or equal to 5. And 3, prove true for n is equal to k plus 1. So we're going back up here and we're putting in k plus 1. 2 to the power of k plus 1 is greater than is greater than k plus 1 to be squared. Just up here. Okay, so instead of n you're putting k plus 1, instead of n here you're putting k plus 1. So we're proving that true. Now, we're going to rewrite this, so 2 to the power of k plus 1 is 2 to the power of k by 2 to the power 1. 2 to the power k by 2 to the power 1. Now, go back to your assumption, okay? If 2 to the power of k is bigger than k squared, then instead of the 2 to the power of k here, I can replace that with k squared. If that is bigger than that, then replacing it won't change it, okay? So instead of the 2 to the power of k here, I'm replacing it with k squared by 2. Okay, I've assumed that the left is bigger than the right. 2 to the power of k is bigger than k squared. Now down here, if I have 2 to the power of k, well, I can replace that with something smaller and it's not going to change. Okay, and that is bigger than, I'm just going to work this all out here. So square the first, product of the two multiplied by 2, square the last. So what I end up with is 2k squared, bring all of these over, minus k squared minus 2k minus 2 is greater than 0. So I get k squared minus 2k minus 2 is greater than 0.
Miss,
Yes.
square the 1, how did you get 2?
I didn't. Thank you. That's perfect, thanks. Thank you, that makes more sense. Yeah. Okay, so I have k squared minus 2k minus 1. Now, ideally, I'd like it to be something squared over here is greater than 0, because I know that's true. Okay, so I'm looking to get something squared. Now, the first thing I'm going to look for is it a perfect square. So for it to be a perfect square, it would be the square root of this number and the square root of this number. Okay? Now, because that's a minus, I already know that is not a perfect square. Okay? If it was, just for argument's sake, this. Okay? Square root that number, I'd get k. Square root that number, I'd get 1. And because that's a minus, this would be a minus. And then you can check it out and you can say square the first, product of the 2 multiplied by 2, square the last. That's a perfect square. Okay? So I would have been able to replace this with this. In my question, it's not a perfect square, because if it's going to be a perfect square, you're always going to have a plus here. Okay, so that's just something to keep in mind. Basically, you'd be factorising it, and you'd get a perfect square as your answer. Now, I don't have a perfect square. If I factorise it, I'm going to get 2 factors by each other. That's not going to help me. So what you're going to do is you're going to complete the square. Okay? And just go back up to the notes we took down. We write down the formula for completing the square again. Okay, and that is x plus b over 2 minus b over 2. Okay, so half the coefficient of the x and then minus half the coefficient of the x to be squared. So sorry, now this 4 isn't to do with this 4 is from the notes, yeah? So remember we had 1, 2, 3 on the right hand side, this is the 4 there. So using this formula, I'm going to complete the square. So that tells me I do minus b over 2, okay, so it's plus b over 2, but the b is a minus here, to be squared, minus b over 2 to be squared plus c. So that's k minus 1 to be squared minus 2 over 2 is minus 1, minus 1 to be squared is 1, and minus outside of it. So what I end up with, this, k minus 1 to be squared minus 2 is greater than 0. Now, the important thing here is k is greater than or equal to 5. If k is greater than or equal to 5, I get 5 take 1, which is 4 squared. 16 take 2 is 14. 14 is greater than 0. Any number bigger than 5 is going to be bigger than 0. Okay, so the smallest number that k would have to be would be 1 take 1, which is 0, so I get minus 2. That wouldn't work. Okay, so as long as k is actually bigger than 1, I'm fine. My question is k is bigger than or equal to 5, so I'm definitely fine. So what you say here is true. It's true for k is greater than or equal to 5. Therefore, it's true for n is equal to k plus 1. This thing is true. Okay? And then number 4, you have to write out all the words again. Okay, so, but just be careful, because again, we're talking about n is 5 or higher. So what we say is true for n is equal to 5. Must be true for n is equal to 5 plus 1, which is 6. True for n is equal to 6, etc. Therefore, true for all values of n greater than or equal to 5, and n is a natural number. Okay, so just don't forget your statement at the end. Alright, is that okay?
For these ones, would you usually end up completing the square set?
You're generally completing the square or getting a perfect square. You're trying to get that something is squared so that you can show that it's greater than or equal to 0. Yeah. Or you're just trying to manipulate it so that you can definitely show that the left is greater than the right, or whatever the question asks. Okay, but yeah, normally it's the showing that something is squared that will really help you if you can get to that point. Okay, now I am going to do one here that doesn't really use that. We have to use our assumption a little bit more. Okay, so can I get rid of this? Let's go example 2. Okay, prove that n factorial is greater than 2 to the power of n. N is bigger than or equal to 4, and n is a natural number. So, number 1, prove true for n is equal to, what did they tell me, greater than or equal to 4, so n is equal to 4 is the one that I show first of all. Okay, so that means 4 to factorial is greater than 2 to the power of 4. Okay, so 4 by 3 by 2 by 1 is 24, and 2 to the power of 4 is 16. So 24 is greater than 16, that's true. Okay, assume true. So we're assuming true for n is equal to k, and k is bigger than or equal to 4. So instead of n, replace with k. So we're assuming that to be true, okay? K factorial is bigger than 2 to the power k. Now we're going to show it true for n is equal to k plus 1. So back up here, k plus 1 factorial is greater than 2 to the power of k plus 1. Okay. What are we going to do with the k plus 1 factorial? We can rewrite this to be able to use our assumption, okay? So k plus 1 factorial is the same as saying k plus 1 by k factorial. And that's bigger than, over on this side, I have 2 to the power of k plus 1. So that's 2 to the power of k by 2 to the power of 1. Now, my assumption is that k factorial is bigger than 2 to the power of k. So instead of k factorial, I can replace that with 2 to the power of k. So I'm left with k plus 1 by 2 to the power of k is greater than 2 to the power of k by 2. Now I know that k is a positive, okay? I can divide both sides by 2 to the power of k, just cross them off. K plus 1 is greater than 2. Is that true if k is 4 or higher? Like if it's 4, you get 4 plus 1, 5 plus 1, 6 plus 1. That is always true, okay? True for k greater than or equal to 4. Therefore, it's true for n is equal to k plus 1. Okay, so you've shown it to be true. Because k has to be 4 or more, well, basically, as long as k isn't, if k was 1, you'd have 1 plus 2 is greater than 2. That's not true. But if k was 2 or 3 or 4 or 5, it would be true. We know it's definitely true because we're only trying to show that it's greater than or equal to 4. So 4 plus 1. Okay, so write out your words. True for all values of n, as long as n is greater than or equal to 4 and n is a natural number. Have you any issues with that? Just to highlight to yourself, this is what has been replaced, okay? And one more example, so.
Miss Bowler, I don't get it, you can just replace them, like I was saying, because they're bigger, but...
Yeah.
Like.
Right, let's say if 5 is greater than 4, down here, let me see. Yeah, so if I know 5 is greater than 4, let's assume I'm up here, okay, 5 is greater than 4. Now down here, if I have 5, if I replace it with the 4, because 5 is greater than 4, I haven't actually changed anything on this side. Let me get a better example for that.
Okay.
Yeah, give me 2 minutes, okay? I'll do this one and then I'll come back to it because that's not a great example to show you. Yeah, give me 2 seconds, okay? Let's just do example 3. Okay, so prove that 1 plus x to the power of n is greater than or equal to 1 plus nx. So n is greater than or equal to 1, and n is a natural number, and x is a real number. So we're trying to prove this. In this case, n is greater than or equal to 1, so we're just going to show it true for n is equal to 1. So 1 plus x to the power 1 is greater than or equal to 1 plus 1 times x. So I've just filled in 1 instead of n. And 1 plus x, because it's to the power 1, is greater than or equal to 1 plus x. So that is true. Okay, assume true. So 1 plus x to the power of k is greater than or equal to 1 plus k times x. Alright, now show true for n is equal to k plus 1. So back up here, we're just replacing k plus 1 everywhere instead of n. Okay, down here I have a power, so it's 1 plus x to the power of k plus 1. So that means 1 plus x to the power of k by 1 plus x to the power of 1. Okay, my bases are the same and I'm multiplying, so I add my powers. And that's greater than, and that's just 1 plus kx plus x. Just multiply that out there. Now, I know that this here, this is greater than this. So I'm going to replace it down here, okay, with my 1 plus kx. Now we're just going to multiply it all out, okay, first number, second bracket, second number, second bracket, so I get 1 plus x plus kx plus kx squared. Just multiplying out the left hand side. Now, bring all them over and you end up cancelling the 1's and the x's and the kx. Okay, so you're left with kx squared is greater than or equal to 0. Now, k has to be greater than or equal to 1. So, because k is greater than or equal to 1, it doesn't matter what x is, because x to be squared is always going to be positive. So this whole thing is always going to be positive. Okay, so kx squared greater than or equal to 0 is true for k is greater than or equal to 1. As long as k is 1 or more, that thing is true. Therefore, it's true for n is equal to k plus 1. And then you're just going to say it all again. Okay, therefore it's true for all values of n greater than or equal to 1, and n is a natural number.